In 2012, physicists at CERN made one of the greatest discoveries in the history of science. They found the Higgs boson. They measured its mass, and that measurement confirmed a prediction made nearly half a century earlier. But here is what almost nobody talks about. That mass, that specific number, opens one of the most disturbing unsolved problems in all of physics. Not because it is wrong, not because it contradicts anything we expected to find, but because when you sit down and actually calculate what that mass should be, using the very same equations that predicted the Higgs boson in the first place, the answer you get is not just slightly off. It is catastrophically, almost absurdly wrong. The Higgs boson appears to be far lighter than the mathematics says it has any right to be, and after more than a decade of searching, no one can explain why. If you find these kinds of deep questions about the universe fascinating, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now, let's begin. On the 4th of July 2012, inside a packed auditorium at CERN, the European Organization for Nuclear Research near Geneva, Switzerland, something extraordinary happened. Two enormous experimental teams, each consisting of thousands of physicists, engineers and technicians from dozens of countries, independently stood up and announced the same result. They had found a new particle. Not just any particle, the particle that had eluded every experiment on Earth for nearly half a century. The one missing piece from our best and most precise description of how the universe works at its most fundamental level. They had found the Higgs boson. The room erupted. Applause, cheers, tears. Peter Higgs, the British theoretical physicist who had first proposed the particle's existence back in 1964, was sitting in the audience. He was 83 years old. He had spent almost 50 years knowing that his prediction might be right, but having no way to prove it. The technology simply did not exist during most of his career. No accelerator on Earth was powerful enough to produce the collisions needed to create the Higgs boson, let alone detect it. He had waited through decades of planning, decades of construction, decades of incremental progress in experimental physics, all building toward this single moment. When the results flashed onto the screen and the significance of the data became undeniable, Higgs removed his glasses and wiped tears from his eyes. He later said he never truly expected to see the discovery in his own lifetime. This was not the work of a few people. The search for the Higgs boson was one of the largest and most expensive scientific efforts in human history. The machine that made the discovery possible, the Large Hadron Collider, took over a decade to build and cost roughly $10 billion. It sits in a circular tunnel about 27 kilometers in circumference, buried as deep as 175 meters beneath the countryside along the border between France and Switzerland. The tunnel is so large that it passes beneath farms, villages, and the foothills of the Jura Mountains. People go about their daily lives directly above a machine that is recreating conditions from the first moments after the birth of the universe. Inside that tunnel, two beams of protons travel in opposite directions at speeds so close to the speed of light that they complete the entire 27-kilometer circuit more than 11,000 times every single second. Each beam contains billions of protons, organized into tightly packed bunches, and the machine brings these bunches into head-on collisions at specific points around the ring. When two protons collide at these energies, the impact releases so much energy that entirely new particles can materialize from the collision, converting pure energy into matter, according to Einstein's famous relationship E equals mc squared. The particles that emerge exist for inconceivably brief instants, often less than a trillionth of a second, before decaying into showers of other particles. These showers spray outward from the collision point in all directions. Surrounding each collision point are massive detectors designed to catch and measure every fragment, every trajectory, every tiny trace of energy left behind. Two of these detectors, called ATLAS and CMS, are enormous instruments. ATLAS is about 46 meters long and 25 meters in diameter, roughly the size of a 7-story building laid on its side. CMS is smaller in physical dimensions, but actually heavier, weighing about 14,000 tons, more than the Eiffel Tower. These detectors contain millions of individual sensors arranged in concentric layers around the collision point, each layer designed to measure different types of particles. They record data from hundreds of millions of collisions every second, generating a flood of information so vast that sophisticated algorithms must filter it in real time, keeping only the most potentially interesting events for analysis. Both ATLAS and CMS were specifically designed with the Higgs boson as a primary target, and after sifting through the debris of trillions upon trillions of collisions accumulated over months and years of operation, both teams found the same unmistakable signature: a new particle with a mass of about 125 giga-electron volts. Now, giga-electron volts might sound like an unfamiliar unit, but in particle physics, it is the standard way to express mass. Because Einstein showed that mass and energy are equivalent, particle physicists measure mass in units of energy. 1 giga-electron volt is 1 billion electron volts. An electron volt is the amount of energy an electron gains when it moves through an electrical potential of 1 volt. It is a tiny amount of energy by everyday standards, roughly the energy of a single photon of visible light. But when you scale it up to billions of electron volts, you enter the regime where fundamental particles live. 125 giga-electron volts translates to a mass roughly 133 times that of a single proton. In everyday terms, this is extraordinarily small. The Higgs boson weighs roughly the same as a single atom of cesium or xenon. A speck of dust contains trillions upon trillions of times more mass. But in the world of fundamental physics, this particular value turns out to be deeply, disturbingly puzzling. Not because it is wrong, because it is far too light. The discovery confirmed a prediction that had been made independently by 3 groups of physicists in 1964. Peter Higgs published one of the key papers. François Englert and Robert Brout published another slightly earlier. Gerald Guralnick, Carl Hagen, and Tom Kibble published a third. All of them, working from different angles and using different mathematical approaches, arrived at essentially the same conclusion. There must exist a field that fills all of space, a field unlike any other, and that field must have an associated particle. That particle is what we now call the Higgs boson. In 2013, Peter Higgs and François Englert were jointly awarded the Nobel Prize in Physics for their theoretical work predicting the mechanism. Robert Brout had sadly passed away in 2011, just 1 year before the discovery he helped make possible. So the Higgs boson was predicted, searched for across decades, and found. Its mass has been measured with extraordinary precision. Subsequent runs of the Large Hadron Collider, including a major upgrade that increased the collision energy, have only confirmed and refined that number. As of the most recent measurements, the Higgs boson mass sits at approximately 125.25 giga-electron volts, with an uncertainty of only about 0.2 of a giga-electron volt either way. This is not an elusive quantity. This is not a mystery particle with an unknown mass. This is one of the most precisely determined values in modern experimental physics. And that is exactly where the problem begins. To understand why the Higgs boson's mass creates such a deep tension, you need to understand the framework it belongs to and the role it plays. That framework is called the Standard Model of Particle Physics, and it is, without exaggeration, the most successful and most precisely tested scientific theory ever constructed by human beings. The Standard Model describes the fundamental building blocks of the universe and the forces that govern how those building blocks interact. It explains how atoms hold together, how light behaves, how radioactive decay works, and how the nuclear reactions inside stars convert hydrogen into helium and release the energy that makes life on Earth possible. It covers everything from the behavior of individual subatomic particles to the processes that power the Sun. And it has been tested against experimental data for over 50 years. Its predictions have been confirmed by thousands of experiments conducted at laboratories across dozens of countries, often to breathtaking precision. Some of its predictions have been verified to better than 1 part in 10 billion, a level of accuracy that is almost unheard of in any branch of science. To appreciate this, consider that if you were measuring the distance from New York to Los Angeles, and your measurement was accurate to 1 part in 10 billion, your answer would be correct to within a fraction of the width of a human hair. That is the level at which the Standard Model has been tested. It works. It works spectacularly. And this success is precisely what makes the problem with the Higgs mass so uncomfortable. The theory is not failing. The theory is working beautifully. And yet it contains something that, by its own internal logic, should not be the way it is. The Standard Model organizes all known fundamental particles into a surprisingly compact catalogue. There are 12 matter particles, divided into 2 families. The first family is the quarks. Quarks are the building blocks of protons and neutrons, the particles that make up the nuclei of every atom. There are 6 types of quarks, sometimes called flavors. They are named up, down, charm, strange, top and bottom. Of these, the up and down quarks are by far the most important for everyday matter. Every proton consists of 2 up quarks and 1 down quark, held together by the strong nuclear force. Every neutron consists of 1 up quark and 2 down quarks. Every atom in your body, every atom in the Earth, every atom in a distant star is built from up and down quarks, arranged into protons and neutrons. The other 4 quarks, charm, strange, top and bottom, are heavier and unstable. They are produced in high-energy collisions, but decay rapidly into lighter quarks. The top quark, discovered in 1995, is the heaviest of all. It has a mass about 185 times that of a proton, making it roughly as heavy as an entire atom of gold. This will become significant later because the top quark's enormous mass plays a central role in the puzzle we are exploring. The second family of matter particles is the leptons. The most familiar lepton is the electron, the tiny negatively charged particle that orbits atomic nuclei and makes chemistry possible. Everything you see and touch, every color, every material, every chemical reaction, every electrical signal in your brain is ultimately shaped by how electrons behave. The muon and the tau are heavier, unstable versions of the electron. Each of the 3 charged leptons has an associated neutrino. Neutrinos are extraordinarily light, electrically neutral particles that interact with other matter so weakly that they are essentially invisible. Trillions of neutrinos pass through your body every second, produced by nuclear reactions in the Sun, and virtually none of them ever interact with a single atom inside you. Then there are the force carriers. In the Standard Model, forces between particles are not mysterious pushes and pulls acting at a distance. They are mediated by the exchange of specific particles. The electromagnetic force, which governs electricity, magnetism, light, and the interactions between charged particles, is carried by the photon. Photons are massless and travel at the speed of light. Every time you see something, you are detecting photons that have bounced off an object and travelled into your eyes. The strong nuclear force, which binds quarks together inside protons and neutrons and holds protons and neutrons together inside atomic nuclei, is carried by particles called gluons. There are 8 types of gluons. The strong force is enormously powerful. At short distances, it is about 100 times stronger than the electromagnetic force. It is what holds atomic nuclei together against the electromagnetic repulsion between positively charged protons that would otherwise blow them apart. The weak nuclear force is responsible for certain types of radioactive decay and plays a critical role in the nuclear reactions that power stars. It is carried by three particles called the W+ boson, the W- boson, and the Z boson. These force carriers are unusual. Unlike photons, which are massless, and gluons, which are also massless, the W and Z bosons are heavy. The W bosons each weigh about 86 times as much as a proton. The Z boson weighs about 97 times as much. This is a crucial detail. The masses of the W and Z bosons are directly tied to the Higgs field. Without the Higgs field, these particles would be massless, and the weak force would behave in a fundamentally different way. It would have infinite range instead of being confined to distances smaller than an atomic nucleus. Radioactive decay, as we observe it, would not function. The chain of nuclear reactions inside stars would not proceed as it does. The universe as we know it would be unrecognizable. And then there is the 17th particle, the Higgs boson. The last fundamental particle predicted by the Standard Model, and the last to be discovered. It is not a force carrier in the way the photon or the W and Z bosons are. It is not a matter particle in the way quarks and leptons are. It is something different. It is the quantum excitation of the Higgs field, a field that permeates every point in space and interacts with nearly every other particle in the Standard Model. The Higgs field is what gives certain fundamental particles their mass. More precisely, it is the mechanism through which particles like electrons, quarks, and the W and Z bosons acquire mass. Without the Higgs field, all of these particles would be massless. They would travel at the speed of light, never slowing down, never being captured, never forming the stable structures that make matter possible. Without the Higgs field, electrons could not be bound to atomic nuclei. There would be no atoms, no molecules, no chemistry, no solid objects, no stars, no planets, no life. The Higgs field is not just another detail in the equations, it is what makes the material universe possible. Here is one way to think about how it works. Imagine an enormous ballroom filled with people standing around evenly, covering every part of the floor. This crowd represents the Higgs field filling all of space. Now imagine someone walks through the room. If no one in the crowd pays attention, the person glides through freely, moving fast and encountering no resistance. That person is like a photon, a particle that does not interact with the Higgs field and therefore has no mass. But now imagine a famous celebrity enters the room. People cluster around them. Every step becomes harder because the crowd keeps gathering, slowing the celebrity down, making it difficult to accelerate or change direction. The celebrity has effectively gained inertia. They have, in the language of physics, acquired mass. Not because they became heavier, but because the field itself is resisting their motion. Different particles interact with the Higgs field to different degrees. The top quark interacts very strongly, so it acquires a very large mass. The electron interacts very weakly, so it acquires a tiny mass. Photons do not interact with the Higgs field at all, so they remain massless and move at the speed of light. The Higgs field is not literally a crowd of people, of course, but the analogy captures the essential idea. Mass is not something baked into particles from the start. It arises from an interaction between a particle and the Higgs field that fills the space around it. Now, here is a detail that will matter enormously for everything that follows. The Higgs field is different from every other field in the Standard Model in a way that has profound consequences. Every other fundamental field, the electron field, the quark fields, the electromagnetic field, the gluon fields, all of them have a value of 0 in their lowest energy state. When nothing is happening, when no particles are present, when the universe is in its quietest possible configuration, these fields settle to 0. They are calm. They are off. The Higgs field does not do this. In its lowest energy state, the state the universe naturally relaxes into, the Higgs field has a non-zero value everywhere in space. It is never zero. It is always on. This might seem like a strange property, but it is absolutely essential. If the Higgs field sat at zero like every other field, it could not give mass to anything. Its non-zero resting value, what physicists call a vacuum expectation value, is precisely what allows it to interact with particles and grant them mass. This non-zero value is also what breaks a deep symmetry in the underlying equations, a symmetry that, at very high energies, unifies the electromagnetic force and the weak nuclear force into a single entity called the electroweak force. Below a certain energy scale, the Higgs field's non-zero value shatters this symmetry, giving mass to the W and Z bosons while leaving the photon massless, splitting one unified force into two distinct forces with very different behaviors. This process is called electroweak symmetry breaking, and it is one of the most important events in the history of the universe. The Higgs boson itself is a ripple in this ever-present field. The Higgs field fills all of space with a steady, non-zero value. When you violently disturb that field, when you concentrate enough energy in a small enough region by smashing protons together at nearly the speed of light, you can create a brief vibration in the field. That vibration is the Higgs boson. It flickers into existence for an absurdly short time, roughly 10 to the minus 22 seconds, and then decays into other particles. But during that fleeting instant, it is real, it is measurable, and its properties, including its mass, can be recorded. And here is where the trouble quietly begins. The Higgs boson is what physicists call a scalar particle. This is a classification based on a quantum mechanical property called spin. Spin is not literally the particle rotating like a top. It is an intrinsic quantum property that determines how the particle transforms under rotations and how it interacts with other particles. Every particle in the Standard Model has a specific spin. Quarks and leptons all have a spin of 1/2. They are called fermions. Photons, gluons, and the W and Z bosons have a spin of 1. They are called vector bosons. The Higgs boson has a spin of 0. It is the only fundamental particle in the entire Standard Model with a spin of 0. That is what makes it a scalar. This might sound like a minor bookkeeping detail. It is not. In quantum field theory, spin determines something far more important than classification. It determines how vulnerable a particle's mass is to the invisible influences of the quantum world. And the quantum world is not quiet. Even empty space, even a perfect vacuum, is seething with activity at the quantum level. Virtual particles flicker in and out of existence constantly, appearing for unimaginably brief instants before vanishing, interacting with everything around them while they exist. These fleeting quantum fluctuations are not hypothetical. Their effects have been measured in laboratory experiments. They subtly shift the properties of real particles, including their masses. Every particle in the Standard Model is affected by these quantum corrections, but not all particles are equally affected. Fermions, with their spin of 1/2, carry a deep mathematical structure called chiral symmetry that limits how much quantum corrections can shift their masses. Gauge bosons, with their spin of 1, are protected by gauge symmetry, another powerful mathematical shield. These symmetries act as guardrails, preventing the quantum corrections from pushing the masses of these particles to extreme values. The corrections exist, but they are kept under control. The Higgs boson has no such protection. With a spin of 0, the Higgs is the only fundamental scalar in the Standard Model, and scalar particles are uniquely exposed to quantum corrections. There is no symmetry in the Standard Model that shields the Higgs mass from being dragged to enormous values by the accumulated effects of virtual particles. When you sit down and calculate what these corrections should do to the Higgs mass, when you add up the contributions from every particle the Higgs interacts with, the answer is deeply troubling. The corrections do not nudge the mass slightly. They should overwhelm it completely, pushing it to values that are not just larger, but incomprehensibly, catastrophically larger than what we actually measure. The measured mass of the Higgs boson is 125 giga-electron volts. The energy scales where gravity and quantum mechanics are expected to collide, the scales where the standard model itself is expected to break down, are roughly 10 to the 18th giga-electron volts. That is a factor of roughly 10,000 trillion. The Higgs mass appears to be sitting calmly at 125 giga-electron volts, while the mathematics of quantum field theory says it should be feeling an enormous pull toward a number that is 10,000 trillion times larger. And somehow, all those enormous contributions appear to cancel almost perfectly, leaving behind this quiet, stable, measured value. This is not the standard model being wrong. That is the uncomfortable part. Every prediction the standard model makes about the Higgs boson, how often it is produced, how it decays, the precise ways it interacts with other particles, all of these match the experimental data beautifully. The theory works. It works astonishingly well. And yet it contains this particle whose mass seems to sit in a place that the theory's own internal logic says should be almost impossible to maintain. The Higgs boson was found exactly where the theory said it would be. But the theory cannot explain why that location is stable. It cannot explain why the Higgs boson is allowed to be so light. Physicists call this the hierarchy problem. The name refers to the vast hierarchy, the enormous gap between the Higgs boson's mass and the much higher energy scales where new physics is expected to appear. That gap should not exist without a reason. Something should be protecting the Higgs mass. Some deeper mechanism, some hidden symmetry, some new layer of physics should be stepping in and shielding the Higgs from those enormous quantum corrections. For decades, physicists have believed that this mechanism must exist. Many of them built entire careers developing theories about what it might be. They expected the Large Hadron Collider to reveal it, but the Large Hadron Collider found the Higgs boson, and then, so far, nothing else. No new particles that could explain the hierarchy, no new symmetries, no sign of whatever deeper physics might be keeping the Higgs mass under control. The machine delivered the discovery of the century and simultaneously deepened one of the most uncomfortable silences in modern physics. The Higgs boson is real, its mass is measured, and that mass, by every calculation physicists know how to perform, should not be what it is. To understand why the Higgs boson's mass creates such a deep problem, you need to understand something about how the quantum world actually works behind the scenes. Because the universe, at its most fundamental level, is not quiet. It is not calm. It is not a place where particles sit still and mind their own business. The quantum world is a place of constant, invisible, almost frantic activity, and this activity has consequences, real, measurable, unavoidable consequences that affect the properties of every single particle in existence, including the Higgs boson. In everyday life, you think of empty space as truly empty. A vacuum is nothing. No matter, no energy, no activity, just stillness. But quantum mechanics revealed over the past century that this picture is fundamentally wrong. Empty space, even the most perfect vacuum you could ever create, is churning with activity at scales too small to see directly. Fields are fluctuating. Energy is flickering. Particles are appearing from nothing and vanishing again before they can be detected. This is not poetry or metaphor. This is measured, confirmed physics. These fluctuations are real, and they have been observed indirectly through their effects on the properties of matter. To grasp why, you need to understand the uncertainty principle, one of the foundational rules of quantum mechanics. Werner Heisenberg showed in 1927 that nature imposes an absolute limit on how precisely certain pairs of quantities can be known simultaneously. The most famous version says you cannot know both the exact position and the exact momentum of a particle at the same time. But there is another version of this principle that matters enormously here. You cannot know both the exact energy of a system and the exact duration for which that energy state exists. If a fluctuation lasts only a very short time, the energy involved in that fluctuation can be very large. And if the time window is extremely brief, fantastically brief, the energy can be enormous. This means the vacuum is not empty. At every point in space, for every quantum field that exists, energy is constantly fluctuating. These fluctuations produce what physicists call virtual particles. Virtual particles are not the same as ordinary particles. You cannot catch one with a detector. You cannot trap it in a bottle. A virtual particle appears from the vacuum, exists for an almost unimaginably short time, and then disappears again. It borrows energy from the vacuum and returns it before anyone can notice. Think of it like a brief, unauthorized loan from a bank that is repaid so quickly that the bank's records never show a discrepancy. The loan happened. The money existed briefly. But by the time anyone checks the books, the balance is back to where it should be. These virtual particles are everywhere, all the time, in every cubic centimeter of space. Virtual electrons and positrons flicker around every charged particle. Virtual quarks bubble up near every proton and neutron. Virtual photons and gluons mediate the forces holding matter together. This seething quantum activity is happening right now inside every atom of your body, inside every atom of every star in the sky. And this is not speculation. The effects of virtual particles have been measured in the laboratory with extraordinary precision. One of the most famous examples is the Lamb shift, discovered by Willis Lamb in 1947. Lamb measured the energy levels of hydrogen atoms and found that they were slightly different from what the basic equations of quantum mechanics predicted. The discrepancy was tiny, but it was real and it was persistent. When physicists worked out the math, they discovered that the shift was caused by the hydrogen electron interacting with virtual particles in the vacuum. The electron was surrounded by a cloud of virtual photons and virtual electron-positron pairs, and these fleeting visitors subtly altered the electron's energy. Another measured effect is the anomalous magnetic moment of the electron. The electron behaves like a tiny magnet, and the strength of that magnet can be calculated using quantum field theory. But when you include the effects of virtual particles, the predicted value shifts slightly from the naive calculation. This shift has been measured to better than 1 part in a trillion, and the theoretical prediction, including contributions from virtual particles, matches the measurement with staggering precision. The virtual particles are real. Their effects are real. They are not optional decorations on the theory. They are essential, unavoidable consequences of quantum mechanics. Now here is where it connects to the Higgs boson. Virtual particles do not just subtly adjust the energy levels of atoms or the magnetic properties of electrons. They also affect the masses of fundamental particles. Every particle in the standard model is surrounded by a buzzing cloud of virtual particles, and these virtual particles contribute corrections to the mass that the particle appears to have. The mass you measure in an experiment is not the mass the particle would have in a universe without quantum fluctuations. It is the sum of whatever underlying bare mass the particle starts with, plus all the corrections from its interactions with every virtual particle in the vacuum. This is called renormalization, and it is one of the most important concepts in modern physics. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga worked out the mathematics in the late 1940s and were awarded the Nobel Prize for it. Their framework, called quantum electrodynamics, showed how to systematically calculate the effects of virtual particles on the properties of real particles. Later, this framework was extended to describe the strong and weak nuclear forces as well, eventually forming the full mathematical machinery of the standard model. Here is a way to think about it. Imagine you are trying to weigh yourself on a scale, but you are standing in a room full of invisible creatures that are constantly jumping on and off the scale. Some jump on, adding to the reading. Others jump on and then immediately off, barely affecting it. Still others push down from above, pressing on your shoulders. The number the scale shows is not your true weight. It is your weight plus the accumulated effect of all these invisible visitors. In particle physics, the invisible visitors are virtual particles, and the number on the scale is the measured mass. The bare mass, your actual weight without the visitors, might be completely different from what the scale reads. For most particles, this process works perfectly well. The corrections from virtual particles are real and important, but they are manageable. The mathematics produces finite, sensible answers. This is because most particles in the standard model have symmetries that constrain how large the corrections can be. Remember from earlier that quarks and leptons have a spin of 1/2. They are fermions, and fermions possess a deep structural feature called chiral symmetry. This symmetry does not forbid quantum corrections entirely. It does not say that the mass receives 0 corrections, but it imposes a powerful constraint. It ensures that the corrections to a fermion's mass are proportional to the mass itself. If a particle is light, the corrections are light. If a particle is heavy, the corrections are heavy. But the corrections cannot be wildly, disproportionately larger than the original mass. The symmetry acts as a leash, keeping the corrections under control. Consider the electron. The electron has a mass of about 1/1000th of a giga-electron volt. Quantum corrections from virtual particles nudge this mass around, but because of chiral symmetry, those corrections are proportional to the electron's own mass. The corrections are tiny because the electron is tiny. The measured mass of the electron is close to what you would expect even without carefully cancelling enormous contributions. There is no crisis, no mystery, no uncomfortable fine-tuning. The electron's mass is natural. Similarly, the force-carrying bosons, the photon, the gluons, the W+, the W-, and the Z are protected by gauge symmetry. This is another deep mathematical structure built into the standard model. Gauge symmetry is what ensures that the electromagnetic force works the way it does, that the strong force confines quarks inside protons and neutrons, and that the weak force mediates radioactive decay. These symmetries also protect the masses of gauge bosons from receiving uncontrolled quantum corrections. The photon is exactly massless, and gauge symmetry guarantees it stays exactly massless no matter what virtual particles do. The W and Z bosons have masses, but those masses are set by the Higgs mechanism and protected by the same gauge structure. The corrections are real but constrained. The Higgs boson has no such protection. None. It is a scalar particle, a particle with spin of 0, and in the standard model there is no symmetry that guards a fundamental scalar's mass from quantum corrections. This is not an oversight. It is not something physicists forgot to include. It is a deep structural fact about the mathematics of quantum field theory. Scalar particles are uniquely vulnerable. To see just how different the Higgs boson situation is from that of every other particle, imagine a thought experiment. Imagine you could turn a dial that controls the highest energy scale in the theory, the energy above which unknown new physics takes over. Start with the dial set low, at say 1000 giga-electron volts, just a few times above the Higgs mass. Now slowly turn the dial higher. Push the cutoff to 10,000 giga-electron volts, then to 1,000,000, then to 1,000,000,000, then to 10 to the 12th, then all the way up to 10 to the 18th, the Planck scale. Watch what happens to the electron's mass as you turn the dial. Because chiral symmetry constrains the corrections to be proportional to the electron's own mass, and because the proportionality involves only a logarithm of the cutoff scale, the electron barely notices. As you increase the cutoff by a factor of 1 trillion, the correction to the electron's mass grows by a modest additive amount. The electron remains light. It stays essentially where it started. You could turn the dial all the way to the Planck scale, and the electron would shrug. Its mass is protected. It is safe. Now watch the Higgs boson. As you turn the same dial, the correction to the Higgs mass grows not logarithmically, but quadratically. It does not grow gently. It grows explosively. When the cutoff is at 1000 gigaelectron volts, the correction is already comparable to the Higgs mass itself. When you push the cutoff to 10,000 gigaelectron volts, the correction has grown by a factor of 100. At 1,000,000 gigaelectron volts, the correction is 1,000,000 times larger than the measured Higgs mass. At the Planck scale, 10 to the 18th gigaelectron volts, the correction is roughly 10 to the 26 times the measured value. The Higgs mass has been dragged upward with the cutoff, hauled relentlessly toward whatever the highest energy scale in the theory happens to be. There is no leash, there is no guardrail. The scalar mass is completely exposed, tracking the cutoff like a leaf caught in a gale, while the electron sits undisturbed in the calm. This is the heart of the asymmetry. The electron is protected by chiral symmetry. The photon is protected by gauge symmetry. The Higgs boson is protected by nothing. And the contrast is not subtle. It is the difference between a correction that barely matters and a correction that overwhelms the entire quantity it is correcting by 26 orders of magnitude. When you calculate the quantum corrections to the mass of a scalar particle, the contributions from virtual particles are not proportional to the scalar's own mass. They are proportional to the heaviest energy scale in the theory. And this is where the nightmare begins. Let me walk you through the logic carefully, because this is the heart of the hierarchy problem. The Higgs boson interacts with other particles. In fact, it interacts with almost everything in the standard model. It interacts with quarks, it interacts with leptons, it interacts with the W and Z bosons. And every particle that the Higgs interacts with contributes virtual particle corrections to the Higgs mass. Each correction is like a tug on the Higgs mass, pulling it in one direction or another. Some corrections push the mass higher, others push it lower. But the key point is that the size of each correction depends not on the Higgs boson's own mass, but on the mass and energy scale of the virtual particles involved. Consider the top quark, the heaviest known fundamental particle, with a mass of about 173 gigaelectron volts. The Higgs boson interacts very strongly with the top quark because the top quark derives almost all of its enormous mass from the Higgs field. This strong interaction means the top quark contributes the largest quantum correction to the Higgs mass of any known particle. Virtual top quarks and top antiquarks constantly appear from the vacuum near the Higgs field, flickering in and out of existence, and each appearance tugs on the Higgs boson's mass. The correction from the top quark alone is already a significant number on the scale of the Higgs mass itself. But the top quark is not the problem. The real problem is what happens when you consider the possibility that there are heavier particles or phenomena at much higher energy scales that we have not yet discovered. And there is every reason to believe such things exist. The standard model, for all its success, is almost certainly not the final story. It does not include gravity. It does not explain dark matter. It does not explain why the universe contains more matter than antimatter. It does not explain neutrino masses. It does not unify the three forces it describes into a single underlying force. At some higher energy scale, new physics must exist. The most dramatic scale where we know the standard model must break down is the Planck scale, roughly 10 to the 18th gigaelectron volts. This is the energy scale where gravity becomes as strong as the other forces, where quantum effects in gravity become impossible to ignore, and where our current description of space-time itself is expected to fall apart. The Planck scale is not speculative. It is derived directly and unavoidably from three of the most fundamental constants in all of physics: the speed of light, which governs the structure of space-time, the gravitational constant, which sets the strength of gravity, and Planck's constant, which sets the scale of quantum effects. These three constants have been measured with extraordinary precision through completely independent experiments. When you combine them in the only way that produces a quantity with units of energy, you get the Planck scale. It is as firmly established as any quantity in physics, and the Planck scale represents an absolute ceiling on the energy regime where the standard model, without a quantum theory of gravity, can possibly make sense. At energies approaching the Planck scale, the gravitational force between individual particles becomes comparable in strength to the other fundamental forces. Quantum effects in gravity, effects that the standard model completely ignores, become impossible to neglect. The smooth fabric of space-time that general relativity describes may itself break down into something discrete or fluctuating or fundamentally different from anything we currently understand. Whatever happens at the Planck scale, the standard model as we know it cannot be the correct description. Something new must take over, and whatever that something is, the Higgs boson's mass is sensitive to it. Now here is the critical calculation. When you compute the quantum corrections to the Higgs mass, and you include contributions from virtual particles at all energy scales up to the Planck scale, the result is enormous. The corrections are not proportional to 125 giga-electron volts. They are proportional to the square of the Planck scale. The square of 10 to the 18th giga-electron volts is 10 to the 36 giga-electron volts squared. This correction is not a small nudge. It is a sledgehammer. It should push the Higgs boson's mass up to something on the order of the Planck scale itself, roughly 10 to the 18th giga-electron volts. And yet, the measured mass of the Higgs boson is 125 giga-electron volts. The gap between those two numbers is not a factor of 2 or 10 or even 1,000. It is a factor of roughly 10,000 trillion. The measured Higgs mass is 10,000 trillion times smaller than what the most straightforward calculation suggests it should be. To make this concrete, imagine you have a bank account. Money flows into the account from many different sources, some adding funds, some withdrawing funds, and the individual transactions are enormous. Billions of dollars flowing in, billions of dollars flowing out, massive positive deposits, massive negative withdrawals, transactions from sources you can see, and transactions from sources you cannot fully identify. Now imagine you check the balance, and after all those colossal transactions, the balance reads exactly $12.50. Not roughly zero, not a random large number, but a very specific, small, stable value. You would find this deeply suspicious. How did all those enormous deposits and withdrawals cancel so precisely to leave exactly $12.50? That level of cancellation would be either a staggering coincidence or evidence that someone or something is carefully orchestrating the transactions behind the scenes. This is essentially the situation with the Higgs mass. The quantum corrections are enormous. Positive contributions from certain virtual particles, negative contributions from others, contributions from known particles at accessible energies, contributions from unknown physics at much higher energies. All of these pile up, each one enormous, each one dwarfing the final measured value. And somehow, they all cancel to a precision of roughly 1 part in 10 to the 26th, leaving behind a tiny, stable residual of 125 giga-electron volts. The cancellation required is not approximate. It is exquisite. It is almost perfect. And the standard model provides no mechanism, no reason, no underlying principle that explains why this cancellation should occur. This is what physicists mean when they say the Higgs mass is fine-tuned. Fine-tuning means that the parameters of the theory must be adjusted to extraordinary precision in order to produce the observed result. It is as if nature set the bare mass of the Higgs boson and the quantum corrections to differ by a number that is enormous in both cases, but to cancel in their first 26 or so significant digits, leaving behind only a tiny remainder. That kind of cancellation, without an explanation, makes physicists deeply uncomfortable. There is a way to quantify this discomfort. Physicists use a concept called naturalness. The idea was articulated most clearly by Gerard Tufte in 1980, and later explored extensively by many others. Naturalness is the expectation that the measurable quantities in a theory should be of similar magnitude to the fundamental parameters that determine them. If a measured value turns out to be vastly different from the scale set by the underlying parameters, if it requires extraordinary cancellation between large contributions, then something is probably missing from the theory. Either there is a symmetry you have not discovered, a mechanism you have not identified, or a deeper structure you have not yet uncovered. The theory is not wrong, exactly, but it is incomplete in a way that demands explanation. Think of it this way. If you walk into a room and see a pencil balanced perfectly on its tip, standing upright with no visible support, you do not simply accept it and move on. You assume there must be an explanation. Perhaps there is a tiny hole in the table that the pencil tip is resting in. Perhaps there is glue. Perhaps a thin wire is holding it from above. Something is keeping the pencil balanced, even if you cannot see it immediately. The pencil could, in principle, balance on its own, with exactly the right conditions, on a perfectly smooth surface with zero air currents and no vibrations whatsoever. But that level of perfection would be so unlikely, so unnatural, that you would never accept it without a deeper explanation. You would keep looking until you found the mechanism. The Higgs boson's mass is the balanced pencil. The standard model says it can balance. The equations allow it. There is nothing mathematically inconsistent about the Higgs mass being 125 giga-electron volts. But achieving that value, within the framework of the standard model, requires the kind of miraculous cancellation that physics has historically refused to accept as coincidence. Every other time in the history of physics that a quantity appeared fine-tuned, there turned out to be a deeper reason, a hidden symmetry, an underlying mechanism, a new layer of structure beneath the surface. Consider a historical example that illustrates this beautifully. In the early 20th century, physicists studying atomic nuclei encountered a puzzle about the mass of the neutron. The neutron is very slightly heavier than the proton. The difference in their masses is only about 1 part in 1,000. For a while, this seemed like an accident, a coincidence with no deeper significance. But eventually, physicists discovered that protons and neutrons are not fundamental particles. They are made of quarks, and the small mass difference between the proton and the neutron is explained by the small mass difference between the up quark and the down quark, combined with electromagnetic corrections. What looked like a fine-tuned coincidence turned out to have a perfectly natural explanation once the deeper structure, quarks, was revealed. Physicists expected something similar with the Higgs boson. They expected that the apparently fine-tuned cancellation in the Higgs mass would turn out to have a natural explanation, a mechanism, a symmetry, a new layer of physics that makes the cancellation automatic rather than accidental. They expected that this mechanism would involve new particles or new forces that appear at energy scales not too far above the Higgs mass itself. The logic was straightforward. If the Higgs mass is 125 giga-electron volts, and if there is a mechanism protecting it, that mechanism should become visible at energies of roughly the same order of magnitude. Perhaps a few hundred giga-electron volts, perhaps a few thousand, but not at energy scales trillions of times higher. The protector, whatever it is, should be nearby. This reasoning, known as naturalness, guided decades of theoretical work and experimental planning. It influenced which theories physicists developed, which experiments they proposed, and how they designed the Large Hadron Collider itself. The machine was built to explore the energy range from a few hundred to several thousand giga-electron volts, precisely because naturalness predicted that new physics protecting the Higgs mass should appear in that range. But to understand why physicists were so confident, and why the absence of new physics has been so unsettling, you need to appreciate one more crucial aspect of the hierarchy problem. The issue is not merely that the Higgs mass could be large. The issue is that it is sensitive to every energy scale in the theory, all the way up to the very highest. This sensitivity is what makes the scalar field uniquely dangerous. When physicists compute quantum corrections, they use a mathematical tool called a cutoff. The cutoff represents the highest energy scale at which the theory is valid, the energy above which new, unknown physics takes over. For the standard model, the natural cutoff is somewhere around the Planck scale, because that is where gravity becomes strong and the standard model's framework is expected to fail. But the precise value of the cutoff matters enormously for scalar particles. As we saw with the dial, the correction to the Higgs mass squared grows in proportion to the cutoff squared, not linearly, quadratically. Every time you raise the cutoff by a factor of 10, the correction does not grow tenfold, it grows 100-fold. Raise it by a factor of 1,000, and the correction grows 1,000,000-fold. This relentless scaling is what makes the scalar uniquely dangerous among all the particles in the standard model. Fermion mass corrections grow only logarithmically with the cutoff, barely changing even across vast energy ranges, as we saw with the electron. Gauge boson masses are pinned by symmetry and do not grow with the cutoff at all. Only scalar masses are pulled quadratically, violently, irresistibly, toward whatever the highest energy scale in the theory happens to be. This is the mathematical core of the hierarchy problem. It is not a vague philosophical complaint. It is a specific quantitative statement about how quantum field theory works. The equations of the standard model, the very equations that have been confirmed by thousands of experiments to extraordinary precision, predict that the Higgs boson's mass should be dragged toward the Planck scale unless something intervenes. And the standard model, as it stands, contains nothing that intervenes. There is a subtlety here that is worth clarifying. Some people, when they first hear about the hierarchy problem, wonder whether you can simply choose the bare mass of the Higgs boson to cancel the quantum corrections. Mathematically, you can. There is nothing stopping you from setting the bare mass to an enormous negative value that nearly perfectly cancels the enormous positive correction from virtual particles, leaving behind the small measured value of 125 giga-electron volts. The equations allow this. The math works out. But the cancellation requires adjusting the bare mass to roughly 26 decimal places of precision. You need the bare mass and the quantum correction, two completely independent quantities arising from completely different aspects of the physics, to agree to 1 part in 10 to the 26. There is no physical reason within the standard model for these two numbers to be related at all, let alone to cancel so precisely. It would be like setting the temperature on a thermostat in a room where a furnace is blasting at full power on one side and a blizzard is howling through an open window on the other side, and finding that the room sits at exactly 72 degrees. Not approximately 72, exactly, to 26 decimal places of precision. The furnace and the blizzard, two wildly different independent sources of heating and cooling, would need to cancel almost perfectly. You could accept this as a coincidence, but any reasonable person would assume there must be a thermostat, some hidden mechanism actively regulating the temperature, ensuring the cancellation happens automatically. That is what naturalness demands. Not that the coincidence is impossible, but that it cries out for explanation. And for decades, the physics community took this seriously. They assumed the explanation existed. They assumed new particles, new symmetries, or new structures would be found near the Higgs energy scale. They assumed the thermostat was real and that the Large Hadron Collider would find it. The concept of naturalness also connects to a deeper question about the role of scales in physics. One of the most powerful organizing principles in modern physics is the idea that phenomena at different energy scales should be largely independent of each other. The physics of atoms should not depend sensitively on the physics of galaxy clusters. The behavior of molecules should not require precise knowledge of what happens at the Planck scale. Physics at low energies should be describable without knowing every detail of what happens at high energies. This principle is called decoupling, and it has been remarkably successful throughout the history of physics. You can build an excellent theory of chemistry without knowing anything about quarks. You can build an excellent theory of fluid dynamics without knowing anything about individual atoms. Each layer of reality can be understood on its own terms. The hierarchy problem threatens this principle. If the Higgs mass is genuinely sensitive to physics at the Planck scale, then understanding a low-energy quantity, the Higgs mass at 125 giga-electron volts, requires knowing the precise details of physics at energies 10,000 trillion times higher. Low-energy physics would not decouple from high-energy physics. The scales would be tangled together in an uncomfortable, unnatural way. The Higgs mass would be the one thread you could pull that unravels the neat separation between different layers of physical reality. Ken Wilson, who won the Nobel Prize in 1982 for his revolutionary work on understanding how physics at different scales relates to physics at other scales, formulated this concern rigorously. Wilson showed how the properties of systems at large scales emerge from the details at small scales through a process called the renormalization group. His work made precise the idea that most physical quantities at low energies are insensitive to the details of high-energy physics. But scalar masses are the exception. They are the one type of quantity that refuses to decouple, that stubbornly remains sensitive to the highest scales. Wilson himself was deeply troubled by this and considered it one of the most important unsolved problems in physics. So the hierarchy problem is not simply about one number being smaller than another. It is about the internal consistency of the framework we use to describe nature. It is about whether the universe operates in layers that can be understood independently, or whether one low-energy quantity, the Higgs mass, requires a miraculous conspiracy across every energy scale in existence to have the value we observe. It is about whether the most successful theory in the history of physics contains a crack in its foundations, not a factual error, not a wrong prediction, but a gap in explanation so deep that it suggests something fundamental is missing. The Higgs boson exists. Its mass is measured. The Standard Model accommodates that mass without contradiction. But the Standard Model cannot explain why that mass is what it is. It cannot tell us why the quantum corrections, which should be overwhelming, appear to cancel with extraordinary precision. It cannot point to a symmetry, a mechanism, or a principle that makes the cancellation automatic. The equations work. The predictions match the data. But behind the scenes, the numbers seem to be arranged with a care and precision that the theory itself does not account for. Something is keeping the Higgs boson light, and as of today, no one knows what it is. So the Higgs boson's mass appears to be unnaturally light. The quantum corrections should overwhelm it. The Standard Model provides no mechanism to prevent that, and for decades, physicists looked at this situation and reached a conclusion that felt almost inescapable. If the hierarchy problem is real, if the Higgs mass truly is sensitive to much higher energy scales, then something must exist that we have not yet discovered. Some new particle, some new symmetry, some deeper layer of structure must be stepping in and protecting the Higgs mass from being dragged to catastrophic values. The problem was not just a curiosity to be admired from a distance. It was a signpost. It was pointing toward undiscovered physics, and it was telling physicists exactly where to look. The logic went like this. If the Higgs boson's mass is 125 giga-electron volts, and if something is protecting it from enormous quantum corrections, then whatever is doing the protecting cannot be hiding at absurdly high energies. The protector has to be nearby. It has to operate at energy scales not too far above the Higgs mass itself. Because if the protecting mechanism only kicks in at, say, 10 to the 15th giga-electron volts, then between the Higgs scale and that distant scale, the quantum corrections would still accumulate unchecked. The Higgs mass would still be pulled upward across that entire enormous gap. The fine-tuning problem would simply be shifted rather than solved. For the protection to work naturally, for the cancellation to be automatic rather than accidental, the new physics responsible for it should appear at energies within roughly a factor of 10 or so of the Higgs mass. That means somewhere between a few hundred and a few thousand giga-electron volts. This was an extraordinary claim. It was not just saying that new physics exists somewhere out there at some unknown energy scale. It was saying that new physics should exist at energies that particle accelerators could actually reach. The hierarchy problem was not pointing towards some impossibly distant frontier that humans would never probe. It was pointing directly at the energy range that the next generation of colliders was being designed to explore. This made the hierarchy problem uniquely exciting among unsolved problems in physics. It was not merely philosophical, it was experimentally actionable. You could build a machine and go looking for the answer. And so, for decades before the Large Hadron Collider was even built, theorists developed elegant proposals for what this new physics might look like. Three broad families of ideas rose to prominence. Each approached the hierarchy problem from a different angle. Each proposed a different kind of mechanism for protecting the Higgs mass, and each made predictions, specific, testable predictions about what should appear when collisions reached sufficiently high energies. These were not vague speculations tossed off during coffee breaks. They were detailed mathematical frameworks with concrete consequences, worked out in thousands of research papers published over several decades by some of the most brilliant minds in theoretical physics. And the prevailing expectation, the shared conviction of much of the community, was that at least one of these ideas would be confirmed when the Large Hadron Collider turned on. The most celebrated and widely studied proposal was supersymmetry. For decades, supersymmetry, sometimes affectionately called SUSY, was the leading candidate solution to the hierarchy problem. It was so dominant in theoretical particle physics that generations of graduate students built entire careers around it. Thousands of research papers explored its implications. Entire textbooks were devoted to its mathematics. When physicists talked about what the Large Hadron Collider would discover beyond the Higgs boson, supersymmetry was almost always the first word spoken. The core idea of supersymmetry is breathtakingly elegant. It proposes a new kind of symmetry in nature, a deep mathematical relationship between the two fundamental categories of particles that make up the universe. Remember that every known particle falls into one of two classes based on its spin. Fermions, particles with half-integer spin like quarks and leptons, make up matter. Bosons, particles with integer spin like photons, gluons, and the W and Z bosons, carry forces. In the Standard Model, these two categories are completely separate. There is no mathematical operation that transforms a fermion into a boson, or a boson into a fermion. They are distinct species obeying different statistical rules. Supersymmetry proposes that this separation is not fundamental. It proposes that, for every known fermion, there exists a corresponding boson with the same charges, and for every known boson, there exists a corresponding fermion. The universe, according to supersymmetry, contains twice as many fundamental particles as the Standard Model describes. Every particle has a superpartner. The electron, a fermion, would have a bosonic partner called the selectron. Each quark would have a scalar partner called a squark. The photon would have a fermionic partner called the photino. The gluon would have the gluino. The W and Z bosons would have fermionic partners called the wino and the xeno. The Higgs boson itself would have a fermionic partner called the Higgsino. These names might sound whimsical, but the mathematics behind them is rigorous, precise, and deeply rooted in the structure of quantum field theory. Why would this solve the hierarchy problem? Because of a remarkable mathematical cancellation that emerges directly from the symmetry itself. Remember that the dangerous quantum corrections to the Higgs mass come from virtual particles appearing in the vacuum and tugging on the Higgs field. Virtual fermions and virtual bosons contribute corrections with opposite signs. A virtual top quark, which is a fermion, pushes the Higgs mass in one direction. A virtual top squark, the superpartner of the top quark, would push the Higgs mass in exactly the opposite direction by exactly the same amount. If supersymmetry is exact, if the superpartners have exactly the same masses as their standard model counterparts, then these corrections cancel perfectly. Every dangerous contribution from a fermion loop is exactly offset by the corresponding contribution from a boson loop. The enormous quantum corrections that threaten to push the Higgs mass toward the Planck scale simply vanish. They cancel to zero, automatically, at every order of the calculation. Not because of some accidental numerical coincidence, but because the symmetry of the theory guarantees it. The cancellation is structural, built into the mathematics at the deepest level. This is the extraordinary power of symmetry in physics. When a cancellation is enforced by a symmetry, it is not a lucky accident that might break down under slightly different conditions. It is guaranteed. It happens automatically, no matter what values the other parameters take, no matter how high the energy scale goes. The symmetry protects the Higgs mass the way chiral symmetry protects fermion masses, and gauge symmetry protects the photon's exact masslessness. No fine-tuning is required. The hierarchy problem simply dissolves. But there was an immediate complication. If supersymmetry were exact, if every superpartner had exactly the same mass as its standard model counterpart, we would have already discovered these particles decades ago. The selectron would have the same mass as the electron. We would have seen it in early accelerator experiments. The squarks would have the same masses as the quarks. They would have been produced copiously in any sufficiently energetic collision. We have not observed any of these particles. So if supersymmetry exists, it must be broken. The superpartners must be heavier than their standard model counterparts, heavy enough to have escaped detection in every experiment conducted so far. Broken supersymmetry still helps with the hierarchy problem, but the degree of help depends critically on how heavy the superpartners are. If the superpartners have masses of a few hundred or a few thousand giga-electron volts, the cancellation is not perfect, but it remains very good. The corrections do not cancel to zero, but they cancel well enough that the remaining contribution is comparable to the Higgs mass. The fine-tuning is reduced from 1 part in 10 to the 26 to something far more manageable, perhaps 1 part in 100 or 1 part in 1,000. This is still a coincidence, but a vastly milder one. It is the difference between a pencil balanced on its tip on a perfectly smooth surface in a vacuum and a pencil leaning against a wall at a slight angle. The latter is unusual, but not miraculous. However, the heavier the superpartners are, the worse the cancellation becomes. If the superpartners weigh 10,000 giga-electron volts, the cancellation is much less precise, and the fine-tuning creeps back. If they weigh 1,000,000 giga-electron volts, you are nearly back where you started. The entire point of supersymmetry as a solution to the hierarchy problem was that the superpartners should be light enough to keep the cancellation natural. And natural meant close to the Higgs mass. The expectation, reinforced by decades of theoretical work, was that the lightest superpartners should have masses in the range of a few hundred to at most a few thousand giga-electron volts. Exactly the range the Large Hadron Collider was designed to explore. Supersymmetry also had other deeply appealing features beyond the hierarchy problem. In the minimal supersymmetric standard model, the simplest version of the theory, the three fundamental forces of the standard model, the electromagnetic force, the weak force, and the strong force, nearly converged to a single strength at very high energies. In the standard model without supersymmetry, these forces almost unify, but miss slightly, like three roads that nearly intersect but pass each other by. With supersymmetry, the convergence becomes much more precise. The three forces meet at a single point around 10 to the 16th giga-electron volts, strongly suggesting they might all be manifestations of a single, unified force. This grand unification, long a dream of theoretical physics, seemed to receive powerful circumstantial support from supersymmetry. Supersymmetry also provided a natural candidate for dark matter. Observations of galaxies, galaxy clusters, and the cosmic microwave background have established that roughly 27% of the universe's total mass and energy consists of dark matter, a mysterious substance that interacts gravitationally but does not emit, absorb, or reflect light. No known particle fits this description. But in many versions of supersymmetry, the lightest superpartner is stable and electrically neutral. It would interact only through the weak force and gravity, making it essentially invisible. It would have been produced abundantly in the hot, early universe and would still be present today, pervading galaxies as a ghostly, invisible component. This particle, often called the neutralino, was for decades the leading dark matter candidate in particle physics. So supersymmetry was not just a single-purpose solution to a single problem. It addressed the hierarchy problem, it enabled grand unification, and it provided a dark matter candidate, all simultaneously. These three independent successes made it extraordinarily compelling. Physicists joked, only half kidding, that supersymmetry was too beautiful to be wrong. It seemed to solve too many problems at once for it to be a coincidence. Nature, they believed, must have discovered it first. The second major approach to the hierarchy problem involved extra dimensions of space. This family of ideas proposed that the reason the Higgs mass seems unnaturally light is that our understanding of gravity at short distances is fundamentally incomplete. Perhaps gravity is not intrinsically weak. Perhaps it only appears weak because it is diluted, spreading into additional spatial dimensions that we cannot directly perceive. We experience three dimensions of space: up and down, left and right, forward and backward. But what if there are more? What if additional spatial dimensions exist, curled up so tightly that they are invisible at the scales we can probe? This idea has roots in work by Theodore Kaluza and Oscar Klein in the 1920s, who showed that adding a fifth dimension to general relativity could unify gravity and electromagnetism into a single geometric framework. For decades, extra dimensions remained a mathematical curiosity. Then, in the late 1990s, several groups of physicists realized that extra dimensions could directly address the hierarchy problem. In 1998, Nima Arkani Hamed, Savas Dimopoulos, and Gia Diwali proposed a striking model in which gravity is fundamentally just as strong as the other forces, but it appears weak because it spreads into large extra dimensions that the other forces cannot access. In their framework, all the particles of the standard model are confined to a three-dimensional surface, called a brane, embedded in a higher dimensional space. Everything we can see and touch, every atom, every photon, every electron, is stuck on this brane like writing on a page. But gravity is different. Gravity, being the curvature of space-time itself, is not confined to the brain. It propagates into the full higher dimensional space called the bulk. Because gravity leaks into these extra dimensions while the other forces do not, its strength is diluted across a larger volume. The apparent weakness of gravity, the enormous gap between the gravitational scale and the Higgs scale, is not a fundamental mystery at all. It is a geometric consequence of gravity spreading into dimensions that we cannot directly detect. A different approach was proposed by Lisa Randall and Raman Sundram in 1999. Their model used only one extra dimension, but that dimension had a special geometric property. It was warped. Space-time curved dramatically along the extra dimension, creating an exponential gradient in energy scales. On one end of the extra dimension, the natural energy scale is the Planck scale.
On the other end, where our brain sits, the natural energy scale is exponentially smaller, right around the electroweak scale. The warping of the extra dimension acts like a lens that shrinks energy scales. The Higgs field, living on our brain, naturally has a mass set by the energy scale at our location in the warped geometry. No fine-tuning is needed. A modest amount of curvature in the extra dimension produces an enormous ratio between energy scales on the two ends. A hierarchy that seems unnatural in 3 dimensions becomes a natural geometric consequence in 5. Both versions of extra dimensions predicted observable consequences at the Large Hadron Collider. New heavy particles called Kaluza-Klein excitations would appear, heavier copies of known particles corresponding to vibrations in the extra dimensions. Gravitons might escape into the bulk, showing up as events where energy seems to vanish from the collision without a trace. If the true gravitational scale is low enough, miniature black holes might even be produced in the most energetic collisions. These predictions were dramatic and specific, giving experimentalists clear targets to search for at exactly the energies the machine was designed to reach. The third major approach proposed something even more radical: that the Higgs boson is not a fundamental particle at all. Composite Higgs models suggest that the Higgs is made of smaller, more basic constituents bound together by a new, undiscovered force, similar to how a proton is made of quarks held together by the strong nuclear force. Why would this help? Because composite particles naturally have masses set by the energy scale of their internal binding, not by physics at vastly higher energy scales. A proton has a mass of about 1 giga-electron-volt, but the quarks inside it are much lighter. The proton's mass is determined by the dynamics of the strong force, by the energy scale at which quarks are confined. The proton's mass is natural. It is explained entirely by the physics of its internal structure. No fine-tuning is required, and there is no sensitivity to the Planck scale. Similarly, if the Higgs boson is composite, its mass would be set by the energy scale of the new binding force, rather than by physics at the Planck scale. The Higgs mass of 125 giga-electron-volts would reflect the dynamics of its internal constituents. The hierarchy problem would be solved the same way the proton mass is naturally explained. The Higgs would be light because its internal binding scale is low, and the dangerous sensitivity to vastly higher energy scales would be cut off by its internal structure. The most developed versions of this idea draw on a deep concept from the theory of the strong force, known as QCD. In QCD, there exist particles called pions, composite objects made of a quark and an antiquark. Pions are remarkably light compared to the energy scale of the strong force. Their lightness is not accidental. It is protected by a symmetry called chiral symmetry. When this symmetry is spontaneously broken, it produces light particles called Nambu-Goldstone bosons. Pions are approximately Nambu-Goldstone bosons,
and their small masses are a direct consequence of this approximate symmetry. Composite Higgs models propose that the Higgs boson is a similar kind of object, a pseudo-Nambu-Goldstone boson arising from the spontaneous breaking of a larger symmetry by a new, strong force operating at an energy scale of a few tera-electron volts. The Higgs is light because the approximate symmetry protects its mass. It is not exactly massless because the symmetry is not exact. It is gently broken by the Higgs boson's interactions with standard model particles. But the breaking is mild enough that the Higgs mass remains small. These models also predicted specific signatures at the Large Hadron Collider. If the Higgs is composite, its interactions with other particles should deviate slightly from standard model predictions, following patterns determined by the underlying symmetry structure. In addition, the new strong force should produce heavy resonances at energies of a few tera-electron volts, analogous to the excited states of protons appearing as unmistakable bumps in the collision data. So there were three families of solutions. Supersymmetry, which proposed a vast new spectrum of partner particles whose contributions would cancel the dangerous quantum corrections through a deep mathematical symmetry. Extra dimensions, which proposed that the apparent hierarchy between the Higgs scale and the gravitational scale is a geometric illusion created by the structure of hidden spatial dimensions. And composite Higgs models, which proposed that the Higgs is not elementary, but is made of deeper constituents, its lightness protected by the same kind of symmetry that keeps pions light in QCD. Each approach was mathematically self-consistent. Each addressed the hierarchy problem in a genuinely different way. Each had been developed over decades by physicists of extraordinary talent. And crucially, all three made testable predictions about what should appear at the Large Hadron Collider. The predictions were not identical. Different frameworks predicted different particles, different mass ranges, different decay patterns in the collision data. But they shared one crucial common feature. All of them predicted that new physics should appear at energies within reach of the Large Hadron Collider, roughly between a few hundred and a few thousand giga-electron volts. This was not a coincidence. It was a direct and unavoidable consequence of the hierarchy problem itself. If the hierarchy problem is real, and if a natural solution exists, that solution must operate near the Higgs scale, because operating far above it would simply reintroduce the fine-tuning it was supposed to eliminate. The Large Hadron Collider was designed very deliberately to cover this range. The machine was not built solely to find the Higgs boson. Finding the Higgs was one of its goals, perhaps the most publicized one, but physicists expected the Higgs to be just the opening act. The real drama was supposed to come afterward. The superpartners predicted by supersymmetry, the Kaluza-Klein resonances predicted by extra dimensions, the composite states predicted by the new strong force. Something had to be there. The hierarchy problem demanded it. Naturalness required it. Decades of theoretical reasoning converged on it. The Large Hadron Collider was built to find not just the Higgs boson, but the reason why the Higgs boson's mass is what it is. The confidence was remarkable. In the years before the machine began operations, surveys of particle physicists consistently showed that a large majority expected supersymmetric particles to be discovered. Some were slightly less certain about which specific version of the theory would be realized, but the broad expectation was nearly universal. New particles were coming. The hierarchy problem was about to be solved. The standard model, magnificent but obviously incomplete, was about to be extended into something deeper and more fundamental. There were even public wagers. Prominent physicists bet openly about whether superpartners would appear in the data. Conference talks routinely included optimistic timelines for discovery. Papers were written discussing not whether superpartners would be found, but how to best measure their properties and extract the maximum information once they showed up. Experimental strategies were developed in advance. Analysis tools were refined. The theoretical community had spent decades preparing the interpretive framework needed to make sense of what the machine would reveal. The construction of the collider took over a decade. It was among the most complex engineering projects ever undertaken by human civilization. Thousands of superconducting magnets cooled to temperatures colder than deep space were installed around the 27-kilometer ring. The vacuum inside the beam pipes had to be better than the vacuum of outer space. The detectors had to be assembled from millions of individual components, each tested and calibrated with extraordinary care. The computing infrastructure had to be built to process and store a flood of data, unlike anything science had ever generated. When the machine finally turned on, the physics community held its collective breath. The first low-energy collisions were cautious, exploratory. Then the energy was ramped up, higher and higher. By 2010, the collisions were producing data at energies no laboratory had ever reached. Physicists began searching the collision debris for signs of new particles. They searched for the signatures predicted by supersymmetry. They searched for the heavy resonances predicted by extra dimensions. They searched for the deviations in Higgs behavior predicted by composite models. They searched systematically, carefully, covering every predicted mass range, every decay channel, every corner of parameter space that the theories identified as promising. And in July of 2012, the machine delivered its great triumph. The Higgs boson was found. The decades of theoretical prediction were spectacularly confirmed. The Standard Model's last missing piece fell into place. The auditorium at CERN erupted. The world celebrated. Nobel Prizes were awarded. It was one of the defining scientific achievements of the century. But even as the champagne was being poured, a quieter story was developing in the data. The same collisions that revealed the Higgs boson were also being searched, just as carefully and just as systematically, for everything else that the hierarchy problem said should be there. The partner particles from supersymmetry, the Kaluza-Klein excitations from extra dimensions, the composite resonances from a new strong force. The searches were thorough, sophisticated, and relentless. The experimental teams published result after result, analysis after analysis, covering every major prediction from every major framework. And one by one, the searches came back empty. No squarks, no gluinos, no selectrons, no neutralinos, no Kaluza-Klein modes, no miniature black holes, no heavy composite resonances, no statistically significant deviations in the Higgs boson's measured properties from what the Standard Model alone predicted. The Higgs boson behaved exactly, precisely, stubbornly like the Standard Model said it should, and nothing else appeared alongside it. The energy range where naturalness demanded that new physics must exist was explored with unprecedented thoroughness, and it was empty. The Large Hadron Collider found the Higgs boson. It confirmed the Standard Model's final prediction, and then it fell silent. The machine that was supposed to reveal the mechanism protecting the Higgs mass instead revealed the absence of any such mechanism. The elegant theories that physicists had spent decades developing, the frameworks that seemed too beautiful and too successful to be wrong, were not confirmed. They were not definitively killed either, because theorists could always push the predicted particle masses higher, adjust the parameters, find narrow corners of the models that remained just barely consistent with the data. But the natural, unforced, compelling versions of these theories, the versions that actually solved the hierarchy problem cleanly without simply relocating the fine-tuning, were systematically excluded by the data. The Higgs boson was found, its protector was not, and the hierarchy problem, far from being resolved, became deeper and more uncomfortable than it had ever been before.
The silence that followed the Higgs boson's discovery was not the kind of silence that comes after a question has been answered. It was the kind that comes when the answer should have arrived and did not. The Large Hadron Collider continued running after 2012. It completed its first operational period, then underwent a major upgrade that increased the collision energy from 8 tera-electron volts to 13 tera-electron volts, the highest ever achieved in a laboratory. Then it was pushed to 13.6 tera-electron volts. The machine performed magnificently. It accumulated vastly more collision data than had been collected during the original Higgs discovery run, allowing the experimental teams to search for new particles with far greater sensitivity, probing deeper into the mass ranges where supersymmetric partners, extra-dimensional resonances, and composite Higgs signatures had been predicted to appear. The searches were exhaustive. Physicists at Atlas and CMS did not just run a handful of analyses looking for the most obvious signatures. They conducted hundreds of individual searches targeting different possible particles, different mass ranges, different production mechanisms, and different decay channels. They searched for gluinos decaying into jets of quarks and missing energy. They searched for squarks produced in pairs. They searched for heavy charged particles leaving unusual tracks in the detector. They searched for narrow resonances that would signal a new heavy force carrier. They searched for microscopic black holes that extra-dimensional theories predicted might form in the most energetic collisions. They searched for subtle deviations in the rate at which the Higgs boson decays into various combinations of particles. They applied increasingly sophisticated statistical methods to squeeze every last drop of information from the data. The result, across all of these searches, across every channel and every mass range and every theoretical framework, was the same. Nothing. No new particles, no anomalous signals, no unexplained excesses in the data. Occasionally, a mild fluctuation would appear in one analysis, a small cluster of events that looked slightly higher than the background prediction. Each time, the community would take notice. Papers would be written exploring what the fluctuation might mean. Conferences would buzz with cautious excitement. And then, as more data accumulated, the fluctuation would fade. It would turn out to be a statistical fluke, the kind of random noise that inevitably appears when you perform hundreds of searches simultaneously. One by one, every hint dissolved into nothing. This was not what the physics community had expected. For decades, the prevailing assumption had been that the Large Hadron Collider would discover the Higgs boson and then immediately plunge into a rich landscape of new physics. The Higgs was supposed to be the gateway, not the destination. The discovery was supposed to open a door into a deeper level of reality. Instead, the door opened onto what appeared to be an empty room. The implications took time to sink in. At first, in the years immediately following the Higgs discovery, many physicists remained optimistic. Perhaps the superpartners were just slightly heavier than the initial searches could reach. Perhaps the upgraded machine, running at higher energy and collecting more data, would reveal them. Perhaps the new particles were hiding in unusual decay patterns that required more sophisticated analyses to uncover. But as the years passed and the data accumulated, and the searches grew ever more thorough, the optimism became harder to sustain. The simplest and most natural versions of supersymmetry, the versions that cleanly solved the hierarchy problem with superpartner masses of a few hundred giga-electron volts, were definitively excluded. The data ruled them out, not provisionally, not ambiguously, but conclusively. Supersymmetry was not killed entirely. The framework is so flexible that you can always construct versions where the superpartners are heavier, pushed beyond the current reach of the collider. But each time you push the superpartners heavier, you reintroduce the very fine-tuning that supersymmetry was invented to eliminate. If the lightest superpartners weigh 5,000 giga-electron volts instead of 500, the cancellation between their contributions and those of the standard model particles
is no longer clean and automatic. It requires the kind of delicate numerical coincidence that the theory was designed to avoid. You can still write down the equations, the mathematics still works, but the elegance is gone. The naturalness is gone. The solution to the hierarchy problem, the entire reason supersymmetry was proposed in the first place, is no longer functioning as intended. The same pattern played out for extra-dimensional models and composite Higgs scenarios. The cleanest versions of these theories, the ones that addressed the hierarchy problem most naturally, predicted signatures at energies the Large Hadron Collider has already explored. Those signatures did not appear. More elaborate versions of these models survive, but only by invoking assumptions that push the predicted signals beyond current experimental reach, which amounts to weakening the very feature that made them attractive in the first place. This situation has created a genuine and deepening discomfort within the theoretical physics community. It is important to be precise about what this discomfort is and what it is not. The standard model has not failed. It has not made a wrong prediction. It has not been contradicted by any experiment. In fact, the opposite is true. The standard model has emerged from the Large Hadron Collider era more successful than ever. Every measurement of the Higgs boson's properties, its production rate, its decay patterns, its interactions with other particles, matches the standard model's predictions with impressive precision. The theory works. It works beautifully. And that is precisely the problem. The discomfort is not that the standard model is wrong. It is that the standard model is right without explaining why it is right. The Higgs boson's mass is measured at 125 giga-electron volts. The quantum corrections should push it to catastrophically larger values. The standard model accommodates the measured mass, but only through an apparent cancellation of extraordinary precision. And nothing in the data reveals what is responsible for that cancellation. The theory describes the result correctly, but does not explain how the result comes about. It is as if you discovered a building standing perfectly intact after an earthquake that should have destroyed it, and when you inspected the structure, you found no reinforcement, no earthquake proofing, no hidden supports. The building is standing. Your engineering equations correctly describe its current state, but they cannot explain why it survived. This has led to a profound and sometimes contentious rethinking of some of the core assumptions that guided theoretical particle physics for decades. The principle of naturalness, the idea that measurable quantities should not require extraordinary fine-tuning, had been treated almost as a law of nature. It guided research programs, it shaped funding decisions, it influenced the design of experiments. If naturalness pointed toward new physics at a particular energy scale, that was where you looked. And for good reason. Naturalness had a strong historical track record. Many past discoveries in physics were motivated by naturalness arguments, and those arguments proved correct. But the Large Hadron Collider results have raised an uncomfortable question. What if naturalness is not always a reliable guide? What if the Higgs mass is simply fine-tuned and there is no deeper mechanism protecting it? What if the extraordinary cancellation between the bare mass and the quantum corrections is not a clue pointing toward hidden physics, but simply a brute fact about the universe, a number that happens to take the value it takes without any deeper reason? This question has not landed gently. It has fractured a community that was, for decades, remarkably unified in its expectations. An entire generation of theoretical physicists was trained in the conviction that naturalness was a reliable guide to new physics. Graduate students chose their research problems based on it. Young professors built tenure cases around it. To have spent 20 or 30 years developing the mathematical machinery of supersymmetric models, refining predictions, preparing experimental search strategies, and then to watch the data come in empty is not merely an intellectual disappointment. It is something closer to a professional and philosophical crisis. Some physicists have responded by doubling down. They argue that the superpartners are simply heavier than the current machine can reach, that the Large Hadron Collider explored the easy territory, and that the real discoveries lie just beyond the horizon. They point out, correctly, that absence of evidence is not evidence of absence. The collider has explored up to a few thousand giga-electron volts. The superpartners could be at 5,000 or 10,000. Ruling out a theory requires exploring its full parameter space, and that has not been done. These physicists advocate for more powerful machines that would push the energy frontier higher. Others have responded by questioning the premise. They argue that naturalness was never a law of nature, only a heuristic, a rule of thumb that happened to work in certain historical cases. Perhaps it does not apply to the Higgs mass. Perhaps the universe simply is fine-tuned in this respect, and the task of physics is not to explain why, but to understand the consequences. Jan Francesco Giudice, a prominent CERN physicist, wrote an influential book exploring the possibility that naturalness might not be the right guide for the Higgs mass, arguing that the field needed to take seriously the idea that some fine-tunings might be fundamental rather than symptomatic. Still others have taken a third path, searching for entirely new theoretical frameworks that do not fit neatly into any of the pre-existing categories. Perhaps the hierarchy problem has a solution that no one has thought of yet. Perhaps it requires mathematical tools that have not been developed. Perhaps it involves a relationship between gravity and quantum mechanics that current theories cannot capture. Nima Arkani Hamed, one of the physicists who proposed the extra dimension solution in the 1990s, has spoken openly about the possibility that the hierarchy problem might require a completely new way of thinking about quantum field theory itself, one that goes beyond the existing frameworks of naturalness and fine-tuning entirely. The field is, in a real sense, at a crossroads. The old consensus has broken. A new consensus has not formed. And the question that created this situation, why is the Higgs boson so light, remains as sharp as ever. One framework for making sense of fine-tuning is the anthropic principle combined with the idea of a multiverse. The reasoning goes like this. If the laws of physics allow for many different possible universes, each with different values of the fundamental constants, then the Higgs boson's mass might not be the same in all of them. In some universes, the Higgs mass might be enormous, pushed to the Planck scale by uncontrolled quantum corrections. In others, it might be zero or negative. In a small fraction, the extraordinary cancellation happens to produce a light Higgs boson with a mass near 125 giga-electron volts. Now, most of those universes would not contain observers. A universe where the Higgs mass is at the Planck scale would have completely different physics. Atoms as we know them would not form, stars would not burn, chemistry would not exist. Life, at least life anything like ours, would be impossible. Only in universes where the Higgs mass happens to fall in a narrow range, low enough to allow atoms and chemistry and stars and planets, could beings like us exist to ask the question. So the fact that we observe a light Higgs mass is not a coincidence that demands explanation. It is a selection effect. We observe a fine-tuned Higgs mass because we could only exist in a universe that has one. This argument has a certain logical force, but it is deeply controversial. Critics point out that the anthropic principle, as applied to the hierarchy problem, is not really an explanation. It does not tell you why the Higgs mass has its specific value. It does not predict anything testable. It simply says that the value is consistent with our existence, which is trivially true and scientifically unsatisfying. Critics also worry that accepting anthropic reasoning too readily could undermine the entire enterprise of fundamental physics. If any seemingly unnatural value can be explained by saying we happen to live in the universe where it takes that value, then the motivation to search for deeper explanations evaporates. Why look for a mechanism when you can always invoke selection? Defenders of the anthropic approach respond that these objections, while emotionally resonant, are not scientific arguments. Science is about describing nature as it is, not as we would like it to be. If the universe really does contain a vast landscape of possibilities, and if our observed values really are selected by the requirement that observers exist, then refusing to accept this because it feels unsatisfying is not scientific rigor. It is stubbornness. The debate remains unresolved and is likely to remain so for some time. What is clear is that the old consensus, the confident expectation that naturalness would be vindicated by the Large Hadron Collider, has fractured. The community is no longer united behind a single explanatory framework. Different physicists hold genuinely different views about what the hierarchy problem means and whether it will ever be solved in the traditional sense. Meanwhile, the experimental program continues. The Large Hadron Collider is far from finished. A major upgrade, called the High Luminosity Large Hadron Collider, is underway and expected to begin operations around 2029. This upgrade will not significantly increase the collision energy, but it will dramatically increase the rate at which collisions are produced. Over its planned lifetime, it will accumulate roughly 10 times more data than has been collected so far. This enormous dataset will allow physicists to measure the Higgs boson's properties with far greater precision than is currently possible. Why does precision matter if no new particles have been found? Because new physics does not always announce itself through the dramatic appearance of a new particle in the data. Sometimes it reveals itself far more subtly, through tiny shifts in the behavior of known particles. The Higgs boson interacts with nearly every particle in the standard model, and the strength of each interaction is predicted precisely by the theory. If the Higgs boson is truly alone, a fundamental scalar with no protective mechanism, then its interactions should match the standard model predictions exactly. But if there is new physics lurking just beyond the current reach, perhaps superpartners slightly too heavy to produce directly, perhaps a faint composite structure within the Higgs itself, then the Higgs boson's interactions should deviate slightly from the standard model values. These deviations might be tiny, perhaps a few percent, or even a fraction of a percent. But with enough data, they could be measured. The high luminosity upgrade will push the precision on several key Higgs measurements into exactly this regime. If a deviation is found, even a small one, it would be an earthquake. It would tell us that the Higgs boson is not alone, that there is something else out there influencing its behavior. And the pattern of the deviations, which interactions are shifted and by how much, would give powerful clues about what the new physics actually is. Beyond the current machine, proposals exist for entirely new colliders that would push the energy and precision frontiers far beyond anything achievable today. And understanding how these machines would address the hierarchy problem specifically requires appreciating that there are two fundamentally different strategies for finding new physics, and that they are complementary in a way that neither can replace the other. The first strategy is brute force. Build a more powerful collider, smash particles together at higher energies, and search for new heavy particles that the current machine cannot produce. This is the energy frontier. A proton-proton collider with collision energies of 100 tera-electron volts, roughly 7 times higher than the current Large Hadron Collider, would directly probe mass ranges where heavier superpartners, extra-dimensional resonances, or composite Higgs states might be hiding. If these particles exist with masses of 5 or 10 or even 20,000 giga-electron volts, such a machine could produce them and detect their decay products. The discovery would be unmistakable. A new particle appearing in the data, with measurable mass, spin, and decay properties, would immediately tell physicists what kind of new physics they were dealing with and whether it solves the hierarchy problem. The second strategy is precision. Instead of producing new particles directly, you measure known particles with extraordinary accuracy and look for tiny discrepancies between the measurements and the standard model predictions. This is the precision frontier. A machine optimized for this approach would typically collide electrons and positrons rather than protons. Electron-positron collisions are far cleaner than proton-proton collisions because electrons are fundamental particles with no internal structure. All the energy goes into the interaction, producing events that are precise and much easier to interpret. A high-luminosity electron-positron collider running at the right energy could produce millions of Higgs bosons in a controlled, clean environment, measuring every property of the Higgs to a precision of a fraction of a percent. Why would this matter for the hierarchy problem? Because even if the particles responsible for protecting the Higgs mass are too heavy to produce directly, they would still exist as virtual particles in the quantum vacuum. And as we discussed earlier, virtual particles affect the properties of real particles. Heavy superpartners, even ones weighing 10,000 giga-electron volts, would subtly shift the strength of the Higgs boson's interactions with other standard model particles. The shifts would be small, perhaps 0.5% or less. But an electron-positron Higgs factory, producing millions of clean events, could measure these interaction strengths to a precision of 2 or 0.3%. At that level, even the ghostly fingerprints of particles too heavy to see directly could become visible. You would not discover the new particle itself, but you would detect its shadow, its indirect effect on the Higgs boson. And the pattern of those effects, which interactions are shifted and in which directions, would serve as a kind of indirect portrait of whatever new physics is out there, even if you cannot see it directly. This is why the most ambitious future collider proposals envision machines that combine both strategies. The most prominent example is the Future Circular Collider, or FCC, a proposed machine with a tunnel roughly 100 kilometers in circumference. In its first phase, it would operate as an electron-positron collider, serving as a Higgs factory, measuring the Higgs boson's properties with precision far beyond anything achievable today. In its second phase, decades later, the same tunnel would house a proton-proton collider, reaching collision energies of roughly 100 tera-electron volts. The first phase would tell us whether something is out there. The second phase would tell us what it is. Together, they would mount the most comprehensive assault on the hierarchy problem that physics has ever attempted. Other proposals pursue the same two-pronged logic through different designs. The ILC, the International Linear Collider, would collide electrons and positrons in a straight tunnel several tens of kilometers long, optimized for precision Higgs measurements. The CLIC project at CERN would push electron-positron collisions to higher energies, extending both the precision and the direct search reach. A muon collider, still in the early stages of research and development, would collide muons instead of electrons, potentially combining the clean collision environment of a lepton machine with the high energy reach of a proton machine in a single facility. Each of these machines would approach the hierarchy problem from a different angle, but all of them share the same underlying question. Is there something beyond the standard model protecting the Higgs mass? And if so, what does it look like? There are also indirect approaches that do not require building new colliders at all. Measurements of rare particle decays, searches for electric dipole moments in electrons and neutrons, precision studies of the anomalous magnetic moment of the muon, all of these can be sensitive to virtual effects from new particles too heavy to produce directly. If a superpartner or an extra-dimensional resonance exists just beyond the reach of the Large Hadron Collider, its virtual effects might still leave detectable traces in these precision measurements. Several experiments around the world are pursuing exactly this strategy, pushing the precision of their measurements to levels where even faint whispers of new physics could be heard. Gravitational wave observatories offer another unexpected window. The pattern of gravitational waves produced in the very early universe, during the epoch when electroweak symmetry breaking occurred and the Higgs field first settled into its non-zero value, could carry information about the dynamics of the Higgs field and the nature of the electroweak phase transition. If the transition was strongly first order, producing violent bubbles of the new phase expanding through the old phase, it would generate a background of gravitational waves that future space-based detectors might be able to observe. The character of this signal depends on whether the Higgs sector contains additional structure beyond the minimal standard model. So the search is far from over. The hierarchy problem has not been solved, but neither has it been abandoned. The experimental tools are evolving. The theoretical landscape is being explored from new directions, and the question itself remains as sharp and as urgent as ever. But there is a deeper layer to this story that goes beyond the technical details of collider searches and theoretical frameworks. The hierarchy problem is, at its core, a question about the nature of explanation in physics. For centuries, physics has been driven by the conviction that the universe operates according to principles, that when something appears to require extraordinary coincidence, there is a deeper reason, that fine-tuning is a symptom, never a final answer. This conviction has been spectacularly productive. It led to the discovery of atoms, of quantum mechanics, of the structure of the nucleus, of the standard model itself. Every time a measurement looked unnatural, physicists searched for and eventually found a deeper explanation. The hierarchy problem tests this conviction like nothing else in the history of physics, because for the first time, we have a clear, quantitative, experimentally grounded case of apparent fine-tuning, and the expected deeper explanation has not appeared. The Large Hadron Collider explored the energy range where naturalness said the explanation must live, and it found nothing. This does not prove the explanation does not exist. It might exist at energies just beyond the current reach. It might take a form so unexpected that no one has thought to look for it. It might involve physics so different from anything we have imagined that our current theoretical frameworks cannot even describe it. But it is also possible that the hierarchy problem is telling us something different, something harder to accept. It might be telling us that the universe does not always operate the way we expect, that some quantities are simply what they are, without a deeper mechanism enforcing their values, that naturalness, for all its historical success, is not a universal law, but a heuristic, a guide that works much of the time, but not always. That our aesthetic preferences about what constitutes a satisfying explanation do not constrain what nature actually does. This would not be a failure of physics, it would be a deepening of physics. Understanding where our principles work and where they do not is itself a form of knowledge. If the Higgs mass is genuinely fine-tuned, understanding that fact and its implications would teach us something profound about the structure of the laws of nature. It would tell us that the universe is, in some respects, less constrained than we assumed, that there is more room for apparent coincidence in the fundamental constants than our intuitions suggested. That would be humbling, but it would also be scientifically important. The Higgs boson sits at the center of this question, a real, measured, experimentally confirmed particle with a mass that is known to extraordinary precision, 125.25 giga-electron volts, a mass that the standard model predicts should be unstable against quantum corrections, pulled toward enormously larger values by the accumulated effects of virtual particles at every energy scale. A mass that remains light and stable without any visible mechanism to protect it. A mass that motivated the construction of the most powerful scientific instrument ever built, and that, when the instrument delivered its results, deepened the very mystery it was designed to solve. The Higgs boson was supposed to be the answer. Instead, it turned out to be the question. The most important question in fundamental physics. Why is the Higgs boson so light? Why does its mass sit quietly at 125 giga-electron volts when the mathematics of quantum field theory says it should be screaming upward toward the Planck scale? What, if anything, is keeping it there? We do not know, and that is not a statement of failure. It is a statement of where we stand, at the edge of what we understand, looking out at what we do not. The Standard Model brought us here. It is the most successful theory ever constructed, and it has carried us farther than any previous framework in the history of science. But it cannot take us across this final gap. Something else is needed. A new idea, a new symmetry, a new structure, or perhaps a new way of thinking about what counts as an explanation. And perhaps that is the most remarkable thing about the hierarchy problem. It is not a question that humiliates physics. It is a question that reveals how far physics has come. A century ago, we had not yet discovered even the neutron. 70 years ago, we did not know quarks existed.
50 years ago, the Higgs boson was a speculative idea scribbled in a handful of theoretical papers. Today, we have measured the Higgs boson's mass to a precision of 0.2 of a giga-electron volt, and we have identified, with mathematical rigor, exactly why that measurement creates a problem that our best theories cannot resolve. We understand the question with a clarity that would have been inconceivable to earlier generations. The fact that we do not yet have the answer does not diminish the achievement. It defines the frontier. The Higgs boson is real. Its mass is measured. And that mass remains one of the deepest unsolved puzzles in all of science. It is a puzzle that touches the foundations of physics, the nature of quantum fields, the structure of space-time, the relationship between the very small and the incomprehensibly large. It is a puzzle that may take decades more to solve, or that may reshape what solving even means. And it all comes back to one quiet, stubborn, beautiful fact. The Higgs boson is far too light, and no one can explain why.